Alright, so this is our AP Chemistry Chapter 9 lesson video part 1, and in this video we're going to cover section 9.1 and 9.2. So, hopefully you remember from Honors Chem, we are going back to Vesper. I love Vesper, so really you need to make sure you know those shapes. So because we have already learned this in Honors, I'm not going to slow down very much on the shapes. Okay, so if you need a slower review of Vesper, you need to go back to my Honors videos and watch in chapter 8. It's 8.3 is when I hit Vesper there. Alright, so we're going to go, and so hopefully it comes back to you. So Lewis structures do not indicate the shape of molecules. They simply show the number and types of bonds between atoms. So for example, like a Lewis dot structure might look like this. The overall shape of the molecule is determined by its bond angles, which are the angles made by the lines joining the nuclei of the atoms in the molecules. So for example, a Lewis dot structure might look like this, which might make you think, oh, this bond angle, this is a right angle, this is only 90 degrees. But you have to remember that there's 3D space that these bonds can spread out between. Okay, so just because it's drawn flat on a piece of paper doesn't mean that's what it looks like in reality. So the shape of any particular A, B sub n molecule can usually be derived from one of the 5 basic geometric shapes. So A is just your central atom, B are any of the bonded atoms, and N is the number of bonded atoms. So this could be like CH4 or NH3, like that. That's all this is saying. And so our basic shapes are linear when you have 2 bonding, or if you just have 2 atoms in general. Trigonal planar, this is not actually one of our general shapes, it just happened to be on the picture. Tetrahedral when you have 4 domains. Trigonal bipyramidal when you have 5 domains, and octahedral when you have 6 domains. Those are our 5 basic shapes. So an AB or an AB2 molecule has a linear shape with 180-degree bond angles. So if you have a central atom and 2 bonding atoms, or just 2 bonding atoms, that's going to be considered linear, and a bond angle for linear is 180 degrees. If you have an AB3 molecule, it has trigonal planar shape with 120-degree bond angles. Okay, so trigonal planar can be drawn all in the same plane, so you can draw it flat, and you'll have that 120-degree bond angle for those. And so you'll have 3 domains for trigonal planar. AB4 molecules have a tetrahedral shape with 109.5-degree bond angles. Okay, so this is where we can no longer draw it flat. This is a 3D shape, and so we talked about in Honors how when you have that tripod shape at the bottom, you draw one coming out by a darkened triangular bond and one going back by a dashed line bond. Alright, so CH4 is the perfect example. And so all the bond angles on tetrahedral are 109.5 degrees. That's the only one that's kind of weird number. An AB5 molecule has a trigonal bipyramidal shape with 90-degree and 120-degree bond angles. So again, we can't draw this all in the same plane, so you would draw one of these coming out, one going back. But the bond angle here, remember we talked about in Honors, these are called the axial positions. These are called the equatorial positions. Between an axial and an equatorial, you do have a 90-degree angle. But between your equatorial positions, you have 120. So you can see that over here. So here's a 90-degree angle, but between the equatorial positions, we have 120. So trigonal bipyramidal is the only one where there's 2 different bond angles in the molecule. An AB6 molecule has an octahedral shape with 90-degree bond angles. So again, we usually draw it like this with 2 coming out, 2 going back. And so every bond angle in that molecule is 90 degrees. So moving on to 9.2. So again, that was super fast because we've already covered shapes. So the valence shell electron pair repulsion, also known as Vesper Model, can be used to predict the shape of a molecule based on the fact that electrons repel one another. So that's why when we have something linear, it wants to do like this instead of do like this. Like, why wouldn't that happen if there's only 2 bonding? Well, remember, bonds are made of electrons. So electrons repel one another because they're all negative. So see, they don't want to be this close together unless they have to be this close together. So the bonds and lone pairs, we'll talk about lone pairs here in a minute. The bonds and lone pairs of electrons, bonds and lone pairs are all electrons. They want to be as far apart as possible. Okay, and so that's what happens. So a bonding pair of electrons are located between the nuclei of two atoms that are bonded together. And so as we know, we draw those as a dash. A non-bonding or lone pair of electrons are just located on one atom. And so that's what we draw as our dots. Both pairs represent an electron domain, which is a region where electrons are likely to be found. So when we talk about electron domains, that could be a bonding pair or a non-bonding pair. Double and triple bonds only represent one domain. So if I said, how many domains surround nitrogen? There's 3 bonding domains and 1 lone pair domain. So it's surrounded by 4 domains. However, if I ask how many domains are around carbon, a double bond only counts as 1 domain. So there are 2 domains around carbon. Okay, if I ask how many domains around carbon here, there's 1, 2, 3 domains around carbon, just like that. The best arrangement of electron domains is the one that minimizes the repulsion among the electrons. The arrangement of electrons about the central atom of an ABN molecule or ion is called its electron domain geometry. So when you focus on bonding and non-bonding electrons, when you are determining what the shape of a molecule is, that's referred to as electron domain geometry because you're including every domain. Now we'll focus on molecular geometry when we don't include the lone pairs. So the molecular geometry is the arrangement of only the atoms in the molecular ion. Non-bonding or lone pairs are excluded from the shape. Okay, so you have to be careful. Are you being asked for electron domain geometry or are you being asked for molecular geometry when you answer questions? So the electron domain geometry for NH3 is tetrahedral. Because if you look, NH3 has 4 domains, 3 bonding, 1 non-bonding. 4 domains makes tetrahedral. However, one of them is a lone pair. So it's like you can't see the lone pair. See how there should be a lone pair up here? So if you just looked at the molecule, you wouldn't see all 4 parts. You would just see 3. You would just see that bottom tripod. And so that's called trigonal pyramidal. Okay, so molecular shapes are a little trickier because there's more options than electron domain shapes. So let's look at our options. So if you have 2 bonding and 0 non-bonding, it looks like this, and it is linear with 180-degree bond angles. On the other hand, if you have 3 bonding, 0 non-bonding, looks like this, it's trigonal planar, and you have 120-degree bond angles. However, now we can have lone pairs. So if you have 2 bonding and 1 non-bonding or 1 lone pair, it will look like this, but you can't see those electrons that are by themselves. Okay, we can only see the atoms. So even though it should have a lone pair here, all we would see is this. We're not going to see the lone pair there. So this is called bent. Alright, if you have AB4 and there's 4 bonding, 0 non-bonding, it looks like this. It's tetrahedral, and of course we've already said it has a 109.5 degree bond angle. If you have 3 bonding though and 1 non-bonding, okay, so all we did was we took this and turned one of these into a lone pair. You can't see the lone pair anymore, so you just have the 3 going down, and so that is called trigonal pyramidal because the base of it makes a triangle, but it's kind of a pyramid shape. However, you could have 2 bonding and 2 non-bonding. So see how there's 4 domains? So electron domain geometry is still tetrahedral, but because we can't see 2 of them, it'll look like this. And so again, it is bent. So you can get bent by having 2 bonding and 1 lone pair, or you can get bent by having 2 bonding and 2 lone pairs. So let's look at an example together. I'm starting to wonder if we're ever going to get to any examples. So it says, use the Vesper model to predict the molecular geometry of O3. Okay, so y'all, first I start with just doing the flat shape. Okay, so O has 6 times 3 is 18 valence electrons to work with. Okay, so I'm just going to go 3 in a row. Alright, so I got to make everybody stable. O has 2, so it needs 6 more. This O has 2, 4, so it needs 4 more. This O has 2, so it needs 6 more. But remember, I got to check my total. I'm allowed 18, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I have 2 extra, so I need 1 more bond. But I could put it on this side or I could put it on this side. So remember, that's called resonance. Alright, but I'm going to put it here for now. And so once I add that extra bond, I remove a pair of dots from each atom that touch the bond. Okay, so now everybody's still stable, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, but now I only have 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. But this isn't the true shape, okay, because I have 3 domains. So the farthest apart 3 domains can get is 120 degrees. So in other words, what I would actually need to do is bend my bonds downward. Oh, sorry, my bond didn't really line up with where I put the O. And then I personally, when I'm doing Vesper, I like to balloon out, kind of like, you'll see it on my picture. I kind of like to balloon out the lone pairs because otherwise y'all forget they take up space. Okay, so if you balloon it out, it's hard to forget they take up space. Now this does have resonance, so technically I would need to draw the other one too. And then remember we talked about resonance, so what type of bond order would this have? Well, because you're splitting a single and a double, they each have a bond order of 1.5. But that's not what the question says. It says predict the shape. So this isn't a straight line, it's bent. So my shape for this would be bent, just like that. Okay, so a lot of you'll still call it linear because you forget that those lone pairs take up room. The lone pairs actually take up more room than bonding pairs. We'll get to that later. Alright, so our next one is SnCl3, and there is a little negative right here. Alright, so if you look, Sn is in group 14, so it has 4. Cl is in group 17, so it has 7 times 3. And then remember that negative means I added 1 extra 1. So I have 21, 22 plus 4 is 26 valence electrons to work with. Alright, so my Sn is going to go in the middle. And I'm just going to put my Cl's around it. So Cl only has 2, so each of them is going to need 6 more. Alright, Sn has 2, 4, 6, so it needs 2 more. And then I'm allowed to have 26, and just hint, hint, I have 26. That way I don't have to count it. Okay, but remember, when we have the charge, we need to bracket it and put the charge, but I'm going to wait until I go ahead and turn it into 3D. Okay, so I can see there's 1, 2, 3, 4 domains. That means it's going to take the shape of tetrahedral. So when you draw tetrahedral, you draw 1 up, so I'm just going to balloon my electron pair up. You can draw 1 coming down. Then you draw 1 coming out towards you. And then 1 going back. Just like that. Okay, and then of course it does have a charge, so then I bracket it and put the charge. Now of course the electron domain geometry, because there's 4 domains, the electron domain geometry is tetrahedral, but it asked me for molecular. Remember, I wouldn't be able to see this part. Okay, so when you have the tripod just pointing down, remember it's a triangle on the bottom and it makes a pyramid. It's trigonal pyramidal. Just like that. Alright, so hopefully again this is all coming back to you because we did it in honors. So, bent and trigonal pyramidal. So y'all try the next 2, pause the video, I'll assume you've done that. Oh, but before you pause it, y'all need to do both geometries, electron domain and molecular. So now we can look at how they're different. Okay, so pause the video, I'll assume you've done that and we'll look at it together. Alright, so I have SeCl2. So Se has 6 valence electrons. Cl has 7 times 2. So 14 plus 6 is 22 valence electrons. Se is going to go in the middle because it's the lone one. Cl has 2, so it needs 6 more. This Cl has 2, so it needs 6 more. Se has 2, 4, so it needs 4 more. So I'm allowed to have 22 valence electrons. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So remember, you cannot fix not having enough by adding a multiple bond. To fix not having enough, you just put the extras on that central atom. Okay, so I have no choice but to add those to my Se. Alright. Wait, but that doesn't make any sense. Se shouldn't even have an extra set. Oh, 14 plus 6 is 20. That would be my problem. Okay, I was wondering, I was thinking, I was not expecting this one to be linear because it has 5 domains. Okay, whoops, there we go. Made a mistake. It happens to everyone. Alright, so I'm allowed 20. I have 20. That makes a lot more sense now because now it's going towards more of what I was expecting it to look like. Alright, so I have 4 domains. That means I'm going to have to base it on tetrahedral. Okay, so I put my Se Remember, I always like to do one going up, so I'm going to balloon a lone pair up, one going down, one going out, and one going back. And a lot of you, you'll draw this one in the same plane, and you'll draw it like this instead, which is also fine, as long as you can figure out the shape. Okay, either one of these is fine. It doesn't matter the orientation of it. All right, so it says what's electron domain shape, so I'll just call that electron domain geometry. So I have 4 domains. See, 1, 2, 3, 4. 4 domains is tetrahedral. But then it also asked me for molecular geometry. Well, remember, I couldn't see these two. So it's not linear, it is bent. All right, so hopefully you got that one right. I might have started steering you wrong when I added those 2 extra dots. But I obviously can't add 14 to 6. It happens. All right, so moving on to CO3 with a -2 charge. All right, I'm going to run out of room. I'll go ahead and tell you this has resonance, but I'm not going to draw all 3 of them just because I don't have enough room to get it flat and all that kind of stuff. But it does have resonance. So C is 4, O is 6 times 3, and then I have a -2, so I'm going to add 2 more. So let me make sure I add correctly this time. So I have 18 plus 2, which is 20, plus 4, which is 24. Since clearly I didn't add correctly up here. All right, so my C is going to go in the middle. I'm just going to put my O's wherever. All right, and so now I am going to make everybody stable. So O has 2, so it needs 6. Each O needs 6. And then C has 2, 4, 6, so it needs 2 more. All right, but the problem is I have 26. I'm only allowed 24. So that means I need to add a multiple bond and remove a pair from each atom that touches it. All right, so you know what? I will go ahead and draw the resonance for it. So don't forget, we do need to bracket, but I'm just going to bracket once. Let me go ahead and draw the resonance real quick. I had a little more room than I thought I was going to. And then don't forget, as you're moving that double bond around, make sure that you're altering how many lone pairs you're putting on oxygen. When it has a single bond, it needs 3 lone pairs. When it has a double bond, it only needs 2. And then, of course, I bracketed and put my charge. But remember, it's not actually asking me to draw it. I'm just drawing it for y'all. It's asking you to predict. So what's our electron domain geometry? Well, I have 1, 2, 3 domains, because remember, even a double bond is just 1 domain. So 3 domains is trigonal planar. So I can draw this one all in the same plane. My molecular geometry. Whenever you don't have any lone pairs on the central atom, your electron domain and molecular geometry are the same. Because again, I still just have the 3 domains. So it's also trigonal planar. So the only time that your molecular geometry doesn't match your electron domain is if you have any lone pairs on the central atom. Otherwise, they're the same. All right, so hopefully you got both of those right. Hopefully you knew how to add 14 and 6 and get 20 for this one, unlike me, who got 22. Oh, math. I love it, but, you know, every now and then we make a mistake. All right, so let's talk about some of those bond angles. So we already discussed what they are. Because non-bonding pairs experience less nuclear attraction than bonding pairs, its electron domain is more spread out. So y'all, when you have a bonding domain, it's held in place by 2 nuclei. When you have a lone pair, it's only held in place by 1 nuclei. So that's another reason why you'll see me balloon it out, is I'm trying to remind you it's there, but it also takes up a lot of room. So because lone pairs take up a lot of room, they'll kind of spread out and squeeze some of the bonds a little closer together. So as a result, the electron domains for non-bonding pairs exert greater repulsive forces on adjacent electron domains and tend to compress the bond angles. Okay, so normally the tetrahedral bond angle is about 109.5, but once you have a lone pair, it kind of squeezes those together a little bit, and now it's only 107. Now, they don't usually expect you to memorize what it would be, but like if they ask, you might just want to say it's less than 109.5. So notice the difference in the bond angles between CH4, so all of them are bonding, so it's 109.5. NH3, we now have a lone pair, so it squeezes these together, so now it's only 107. And water, it has 2 lone pairs, so it really squeezes them together, and so it's only 104.5. So again, they don't expect you to memorize all the bond angles possible. They expect you to know the original one. But if they wanted to ask you about NH3 or water, you would just need to know the bond angle will be less than 109.5. Multiple bonds also represent a larger electron domain. So they contain a higher electron density, so they will also compress bond angles. So here you have 3 different domains, which normally would give you bond angles of 120. But this is a double bond, so it squeezes these together. So notice now this is less than 120. Remember, you're not going to need to know this number. This is less than 120, but now this one is more than 120. Okay, because see, they're trying to get away from this high density by squeezing. So this one becomes less than, this one becomes greater than. And like I said, that's usually what they'll want to know, is less than or greater than, not the actual number itself. When a central atom has 5 electron domains, then the shape is trigonal bipyramidal. There are 2 different positions on this molecule. There's axial and equatorial. So I talked about that when we were going over this a second ago. Your axial is the top and the bottom. Your equatorial are the 3 around the middle. The 2 different positions on this molecule are axial and equatorial. The axial position is at a 90-degree angle from its neighbors, and then the equatorial are at 120 with each other and 90 with the axial. So because of that, if you're going to add a lone pair to a trigonal bipyramidal, you will only add lone pairs to the equatorial positions, never the axial. So the equatorial position experiences less repulsion, so non-bonding pairs will always occupy equatorial. So you would never want to put a lone pair on top or on bottom of trigonal bipyramidal. You always want to pick an equatorial location, so that way it can spread out. And so, for example, SF4, you have a lone pair, and so notice they picked an equatorial position. And then just to let you know, this shape ends up being seesaw. When you have 4 bonding and a lone pair, that's what that shape is. The molecular shape is seesaw. So, speaking of shapes, if you have 5 bonding and 0 non-bonding, this is called trigonal bipyramidal. And so you draw 1 up, 1 down, 1 coming out, like to the side, and then 1 coming out of your paper and 1 going back in your paper. That's how you would draw that. If you have 4 bonding and 1 lone pair, though, it'll look like this. So see, we can't see the lone pair. It will look like this, and that's referred to as seesaw. And then if you have 3 bonding and 2 non-bonding or lone pairs, it would look like this. So see, they're both on the equatorial position. You can't see those, so it makes a T. So it's called T-shaped. And then if you have 2 bonding but 3 non-bonding, again, notice they're all in the equatorial positions. We're back to what we started with. This is just a straight line. It's linear. So now let's move on to 6. So if you have 6 bonding and 0 non-bonding, it's referred to as octahedral. And so again, we draw 1 up, 1 down, 2 coming out of the board, and 2 going back into the board. But if you have 5 bonding and 1 non-bonding, you have a lone pair. Remember, you can't see it. So it looks like this. So see, the bottom of it is a square, but it makes a pyramid because you have this top portion. So it's called square pyramidal. But if you have 4 bonding and 2 non-bonding, it'll look like this. So see, we can't see these. So you still have a square, but now it's all in the same plane. So it's called square planar. So let's look at one together. It says, use the Vesper model to predict the molecular geometry of SF4. All right, so we'll look at this one together. So S has 6, F has 7 times 4, so 28 plus 6 is 34. We'll make sure I'm getting my math right. All right, S is going to go in the middle. So I'll put my F's all around. And so each F has 2, so they're all going to need 6. We're going to do the basic Lewis structure pretty quickly now. We don't have time to spend on that. All right, but if I count, I only have 32. So remember, you can't fix not having enough by a multiple bond. You just have to put the extras on the central atom. And this time it's for real, not like the last time when I messed up. All right, so I can see there's 1, 2, 3, 4, 5 domains. That means I'm going to base it on the trigonal bipyramidal. So I do 1 going up, definitely not a lone pair. 1 going down, it cannot be a lone pair either. Remember, those are my axial positions. I'll do my lone pair ballooning out to the side, and then I'm going to have 1F coming out of the board and 1F going back into the board. So it's going to look like this. But it asked me to predict the molecular geometry. So remember, I wouldn't be able to see this and so that makes it Seesaw. Alright, so let's look at IF5. So I has 7, F also has 7, but I'm going to multiply it by 5, so I have 42 valence electrons. Alright, because I got 35 plus 7, that's 42. I'm telling myself that, not y'all. Alright, so I is going to go in the middle, so I'm just going to put all my F's around it. And each F has 2 electrons from the bond, so each one needs 6. Alright, so when I count though, I have 40. I need to have 42, so my only option is to put 2 more on my central atom. Once I do that, I can see I have 1, 2, 3, 4, 5, 6 domains, so I'm going to base it off of octahedral. So when you draw octahedral, you draw 1 going up, 1 going down. I'm just going to happen to make that my lone pair, it doesn't matter. 2 coming out, and 2 going back. Just like that. Alright, so because I can't see this, I'm going to have a square at the base, but it's a pyramid, so its shape would be square pyramidal. So really, y'all, it's all about knowing the shapes. Drawing it is not what y'all usually have trouble with. You just forget the shapes. So just make sure you know the shapes. Alright, so seesaw and square pyramidal. Alright, so y'all tried these two. Just notice you're doing both geometries, electron domain and molecular. I'll assume you've tried them and paused it, and so we'll look at them together. So we have ClF3. So Cl has 7. F has 7 times 3 for a total of 28 valence electrons. Okay, so we have 21 plus 7. So Cl is going to go in the middle. So I'm going to bond my F's. Each F has 2, so it needs 6 more. Cl has 2, 4, 6, so it needs 2 more. But the problem is I only have 26 right here. I have to have 28, so I'm just going to put 2 more on Cl. So now I have 1, 2, 3, 4, 5 domains. So this is going to be shaped like trigonal bipyramidal. So I put my Cl, 1 goes up, it cannot be a lone pair. 1 goes down, it also cannot be a lone pair. And then my lone pairs have to be equatorial. So 1's going to go out, and then my 2 electron pairs can balloon out. So if you could take this and turn it, you can see it's a T. So my electron domain geometry is just taking into the fact that there are 1, 2, 3, 4, 5 domains. 5 domains is trigonal bipyramidal. Remember, for electron domain, it doesn't matter whether they're bonding or non-bonding. But my molecular geometry is just based on this. So if I took these off, I can see that it has the shape of a T, so it's T-shaped. So hopefully you got that one right. Alright, so let's look at our last one. So it's ICl4 negative. So I has 7, Cl has 7 times 4, and then plus 1 more for that negative. Alright, so we have 28 plus 7, which is 35, plus 1 more, which is 36. So my I is going to go in the middle. I'm just going to put all my Cl's. Ooh, running out of space down here. Each Cl has 2, so it needs 6 more. Oh, that looked like 1. Sorry. And I technically doesn't need anything else. 2, 4, 6, 8. But that's only 32. I have to have 36. So I have to add 2 more pairs to I. So once I do that, I can see I have 1, 2, 3, 4, 5, 6 domains. So of course, if I have 6 domains, I already know my electron domain geometry is going to have to be octahedral. Alright, so let's go ahead and draw it. And I left off the brackets because I'm going to put it once I make it 3D. Okay, so remember, the way you draw octahedral is you do 1 going up, so I'm going to do my lone pair. 1 going down, I'm going to do my lone pair. 2 coming out, so I have my Cl and my Cl. And then 2 going back. Alright, so you can see for molecular geometry, I can't see the top and the bottom, so I'm just going to have a square. They're all in the same plane, so it's square planar. Okay, and I'll go ahead and tell you, I don't see them ask you to draw 3D shapes very much on the free response. It's usually questions in the multiple choice. Like it might say, which of the following has a square planar shape? So you don't have to worry about if your shapes look beautiful. Like I said, usually the flat shape is fine in the free response, unless of course they ask you to draw it of the correct shape, so make sure you can. Alright, so sometimes though we like to ask about large molecules that don't just have one central atom. So when that happens, you can just break it up into sections. So like for example, if I have this large molecule and I just want to know the bond angles around the C, you can just kind of cut off the rest of it and you can say, hey, there's 4 domains around that C. That's going to be tetrahedral. And I know tetrahedral has a 109.5 bond angle. Or if I said, what is the shape that's around the middle C? You can say, oh, well there's 3 domains, so that would be trigonal planar. So I know that that's about 120 degrees. I said about, why? Because one of them is a double bond. Okay, so of course this is actually going to be greater than 120 and this is going to be less than 120. So you can always just write approximately 120. Alright, so let's look at this sample exercise together. So it says, eye drops used for dry eyes usually contain the water-soluble polymer called polyvinyl alcohol, which is based on the unstable organic molecule called vinyl alcohol. So this is vinyl alcohol right here. Predict the approximate values for the HOC and the OCC bond angles. Okay, so in other words, we're looking HOC, so we're looking at this bond angle, and OCC, so then we're looking at this bond angle. Okay, so they're going to give you the flat shape. It's gonna look like this is 180 and this is 180, but remember, you have to look at the geometry. Okay, so let's do our HOC bond angle first. So let's not even look here. Okay, so just cover up all of this. On my O, I have 1, 2, 3, 4 domains. That means I'm looking at tetrahedral, which means it's not a 180 bond angle, it's actually 109.5. But if we're being super specific here, 2 of them are lone pairs. So it's going to take that 109.5 and squeeze it together. So I would actually put less than 109.5. Alright, so now let's look at our OCC bond angle. So we're going just like this. Okay, so I just cut all this off. I have 3 domains around carbon. So of course that's normally 120 degrees, even though it looks like 180. Alright, there's 3 domains, that's about 120. Now of course one of them is a double bond. Okay, so if we're looking at here to here to here, that double bond is going to pinch these closer together. So this would actually be greater than 120. Okay, now I notice when I'm looking at when they ask about bond angles on most of the free response questions that I've seen, it seems like they'll just accept 120, even if it's like slightly more or slightly less than 120. But still, I just like to be specific as possible. Alright, so you try this one. I'll assume you've done it and we'll look at it together. So it says predict the HCH, that should say and. Forgot my end there. So we're looking at this bond right here and the CCC bond. So we're looking at this bond right here. Okay, so let's do the HCH bond first. Okay, so all I do here, we'll erase this, is I'll look at this part. So C is surrounded by 4 domains. So that's tetrahedral. So we're looking at about 109.5 degrees. Alright, but then I gotta look at that CCC bond. So it has 2 domains. It doesn't matter that one's a triple bond. 2 domains, the farthest they can get apart from each other is 180 degrees. Alright, so hopefully you got that one right. And so like I said, it's really easy to call this 90 degrees because of the way they draw it, but they're drawing it flat. Okay, they're not drawing it 3D. Alright, so we're ending there. So hopefully this is all coming back to you. We did Vesper, we did bond angles and honors, and so again, if you need a little bit of a slower review, go back to my honors chemistry section 8.3 videos.